Let's start. Okay, anyway, so look at coming back to the definition of round set. So first we have f of alpha with the square root of 1 minus alpha 1, but it also does have alpha 1 does with some philosophy. And here this set alpha 1 equals 1. That's and I have not rewritten the definition of order because it won't really matter for the remainder of the course. The order of this branch set is 2, right? You turn around this set once, this square root changes its value to minus, then you turn around it again, change it by sign again. So once you turn around this set 2 times, you've returned to the original value. So this would be an example of a function where you have a finite order branch. Well, maybe let's make 3 examples. You could also have f of alpha, not of alpha 1, where this is a branch set, but this is infinite order, right? No matter how many times you turn around it, you will never return to the original value. So really, these 2 examples, you can list how many examples you want for where you just take a function in like one or the other coordinate that is some one complex variable function with a branch set, and you just have it to be constant in the second coordinate, and that gives you an infinite amount of examples for branches. But all of the branches will be just planes, right? So it's what we're a bit of a boring thing, but I think it illustrates nicely what's happening. 3, we can look at something like this, where you have the square root of 1 minus alpha 1 minus alpha 2. Okay, and I will not go into the details as to how to derive the branch set of this, but right, so essentially how you do this, you would have to study all of the square roots separately and then match them together. So yeah, maybe as an exercise proof that this is the branch exercise to prove that the branch set is this. So this is the complexified circle, which you get from the big square root, so to say. But then you also have alpha 1 equal to plus or minus 1, which you get from the square root. What's interesting about this is that if you, depending on the branch, choose for the square, well, not depending, but let's say we choose the branch part to be on the such that the square root always has positive imaginary part. If you would then look at the intersection of this branch set with the real plane, so this is the real alpha 1 and alpha 2 plane, you would find the imaginary real plane. You would find something like this. You have alpha 1 over here, and then you have one part of the complexified circle being here, but then the other part sort of moves under, like on the other copy of C squared. Like so one branch set disappears behind another branch set and then reappears. And you can do that. It's because if you choose the square root to always have positive imaginary part, then well, this determines the sign of alpha 2, of the imaginary part of alpha 2. So you can only have the positive part for the alpha 2 and not the negative part. But of course, if once you turn around this, then the other part of the branch becomes apparent, but then this branch disappears. So don't worry about understanding this. I'm not sure I fully understand the geometry myself, but this is a feature that cannot happen in one complex variable. You can't have this type of interaction between 2 singularities. And for this phenomenon to happen, it doesn't matter whether this is a branch. You have the same thing happening for polar singularity, where you have a pole that's apparent on one side, but then disappears underneath behind the branch side and reappears eventually. So not really super important, but it's something to maybe keep in mind. It's very different from what happens in Diffraction, and this, I think, is a nice example to show it. If you like algebraic geometry, you know, when you have a square root, you can build a three-man surface by looking at the set of all omega, comma, z in C squared, such that omega squared is z. And using the same philosophy, you can try to build sort of the Riemann surface of this thing, which will fit in CQ, and then look, and then you can look at these branch sets as sort of singularities of projecting it down to the alpha 1 and alpha 2 anyway. So, yeah, long story short, these are absolutely all branch sets, but depending on where you are, you only see parts of it. It's a bit of an explanation, but okay. You understand these examples? Okay, good. So, then let's move on. Section 4.2. So now we discussed how we need to change integration surfaces to avoid singularities to make sense of 2D Fourier integrals. In a sense that I will explain in a moment. So the grid and arrow. Okay. Okay, so what are we considering? Let f of x this is, yeah, I think this is related to bar up is a version of this would be
okay.
Fine. It really looks the same, but I call it something like this. So we have a spectrum like some function in two complex varieties depending on this parameter. So this is two complex variable Fourier integral. The formula start. And then in this formula, we have the formula for kappa greater than 0, f alpha kappa is as a function of alpha, and then we can in open neighborhood. U, so open in C squared. So is analytic in some open neighborhood of Fourier plane. So this at least is not singular, which is good. And so we also assume that within its domain of analyticity. And I'm not really precise as to what the domain of analyticity is. First of all, it doesn't matter, and second, it will change depending on this parameter. But no matter what for fixed kappa the domain of analyticity is, we assume that f decays sufficiently far. Right. So sufficiently fast means so that everything that we are about to take makes sense. So in particular, this integral is well defined. That's what we assume here. Like in practice, it's enough for it to decay like 1 over alpha 1 times alpha 2, as alpha 1 and alpha 2 go to infinity, but it doesn't matter really how exactly.
You're thinking of f as being in the Schwartz class, for example?
Oh, yeah.
Yeah.
Okay.
Okay.
But we can even think of it as like as being nicer.
Okay.
So, but wait, no, sorry, Schwarz class is absolutely.
It's fine.
Yeah,
Okay.
it's not only fine, it's super nice.
Okay.
In general, it will not be in the Schwarz class.
Ah.
But it will still make sense. But Schwarz class would be one example that you could think about. Okay, and then we assume this also different way that F has possibly, well, not necessarily, everything that follows would also make sense if F has no singularities, but then it would really be a bit boring. So F has possibly some irreducible singularities, right? Irreducible means that the set that describes the singularity is described by as the zero set of some irreducible polynomial. Some irreducible singularities. Sigma j in C squared. Yeah, and of course, we assume, well, not we assume, but the singularity, which is in C squared, will in general depend on the parameter kappa.
But nonetheless, that integral is well defined and meaningful. I mean, the integrals even.
Yeah, because for kappa greater than 0 is well defined. Because we assume that for kappa greater than 0, it is analytic in the neighborhood of the real plane. So for kappa greater than 0, none of these singularities will intersect with the plane.
Ah, okay.
So that means that sigma j.
Right. So the singularities are outside of U.
Yes, exactly. Is the prefix of some j being some polynomial in alpha 1 and alpha 2. And of course, we assume that sigma j is either a polar or branch, so it's only the type of singularity that introduces this. Branch. Okay, so now that as kappa goes to 0 from above, the intersection of sigma j 0 with the real plane is no longer the empty set. So the question that we want to answer is how to, well, how do we define f of x 0? And in some sense, what we do is exactly what we did in the one-context variable setting, using our ZP coordinate system. So the idea is to just look at it all in the Z plane and then mimic what we did in the one-context variable setting. Okay. Okay. We have this set A, J to be equal to the.
Valentin,
Yeah.
do you have any particular, say, specific example of a capital F in mind? We can take a look at to just get a sense.
Well, yes.
Maybe later you'll give us an example.
Well, so the two applications we have in mind is are some diffraction problems for which we need the complex variable setting. You could take, if you want to look at an example, F to be 1 over, let's say, you could look at this.
See.
That is, yeah, this is not singled out in the real plane. It declares sufficiently fast for the integral to make sense. But as kappa goes to 0, the integral would no longer make sense.
I see.
Because you have two Corner singularities. I mean, in this case, it's you can compute it using reciprocal theorems, but pretending that you can't use recipes, then how would we define it? And you can look at.
I see.
Well, it's not such a bad example to keep in mind actually for the rest of today's session. We have these it's A game and B game is this. Sorry, I have not said what A star is for A star in sigma j. Dash. And as a reminder, because we assume that Gj is irreducible, which in particular means that it's that the singularity is regular, which means that the gradient doesn't vanish anywhere, like doesn't completely vanish anywhere on the singularity set. So, long story short, this means that Aj of 0, which we will just call Aj, so whenever we have 0, we just don't bother writing the arguments. So this Aj 0, which we just say is okay.
Sorry, what's the first letter? It's alpha j or
it's Aj. It's supposed to be A.
everything.
But because it's not clear, it's Aj. So yeah, it's just two constants.
Yes.
But they depend on the point A. But for now, we fix some point in our so this is the dash. So it's yeah, so we only look at the intersection, like we want to understand what happens at the intersection of the grid plane and how can we make sense of this integral. So we need this one. And in particular from this, we can see that without loss of generality, we can assume that Aj star is not equal to 0. If it was equal to 0, then Aj star has to be not equal to 0. So this. But this will be really important. So whenever this fails, everything that I'm about to describe has to be repeated for in the other complex plane curve. That will hopefully make more sense in a moment. So now observation. So using the infinite function theorem, we find that there exists a function on in kappa. So kappa alpha 1 beta is a beta kappa such that we get alpha 1 beta kappa alpha 2 star is equal to 0. So alpha star is alpha 1 star. Okay. Is that clear for everyone? Okay, and this is of course because we assume that its derivative doesn't completely vanish anywhere, so it's a function theorem is applicable. So we can find a function like this. And why do we want to find a function like this? Because well, it's very positive. So therefore, lemma that is the intersection of our singularity set with this alpha 2 plane, right? You look at the alpha 2 plane that goes through the point, the singular point that we are considering, is equal to so this intersection is a point, but importantly, well, two things are important. First, it is a point, and second, this intersection is not empty because it's a point. And also, this function is smooth. It's smooth. It depends on kappa, right? And this is again by this function theorem. So now, because the singularity does not intersect the real plane for positive imaginary part of kappa, that means we are either in either of the following situations. We have. So I'll just draw a picture because I think it's better to understand, but it also, well, it should be clear. We have either of the following situations. So this is the alpha 1 plane. So here, this is the real axis, right? This is our integration surface, or in this plane, it is the contour. We have our singular point, alpha 1 star over here. So this is this point. So that will be problematic, but as long as kappa is equal to 0, greater than 0, we have either this, right? Alpha 1 dagger could be above the real axis, and it must be above. If it's above for one value of kappa, it must be above for all values, because otherwise it would have at some point to intersect. And this cannot happen because it can only touch it when kappa is equal to 0. So otherwise we would need some discontinuity. But we know that it's continuous, so it must be above this. Or of course it could be below this. The important part is once you figured out whether it's above or below for one value of kappa, you know that it's above or below for all kappa. That are not 0. So 2, we could have a similar picture in the alpha 2 plane. Sorry, in the alpha 1 plane, but alpha dagger lies down here. And again. This is our integration control. Okay, so but now by our assumption, as kappa goes to 0, alpha 1 dagger will, in the limit, approach alpha 1 star. Simply because, well, alpha 1 dagger of 0 has to be the intersection of sigma j of 0 with this plane, but this must be this point by our assumption. So this arrow illustrates the limit as kappa goes to 0, or here we could have it go to 0 from below. Okay, well, but now we can really just do what we did in the one context for this lesson, right? So we can just change this contour down to make to avoid this problem in the limit. And we change this for kappa greater than 0, which is possible again by Cauchy's theorem applied in the Z plane. And but that's all we need to do to make the position different. Do you understand that? Yes. So and again, this only explains what happens at a single point. In this, we don't describe yet what happens across the whole singularity. But at one point, this picture should. Okay. So it's the other way around. But then for kappa equal to 0, so this is 1, Sorry, there should be 1.1, and this should be picture 1.2. We have picture 2.1, which is again in the alpha 1 plane. And now we change the real axis, something like this. Or we could have 2.2. Okay, something like that. And really, what's important here is we have exactly these two options. So it can't be anything else. So this completely describes all of the possibilities in which we can change our integration pointer, but it also describes exactly how we have to change it to correctly make sense of this integral, right? So if you remember the lesson that we had on the method of series descent for the half-plane problem, it was really important to first understand how are the singularities located relative to our integration contour, because both of these would make sense in the limit. So it's important to understand how we choose, whether we choose one or the other. And which one we have to choose depends on this picture. As an example, work out for this over there what the configuration, like what this picture looks like for this example. Well, I mean, of course, it should be this over here, because it hits it from above. That's positive dimension, like the singularity has positive dimension. And then, of course, if you would look at 1 minus I kappa, you would be in the second picture. So in some sense, this example already describes everything that can happen. But importantly, it also works for a branch set, right? If we have a branch set, then it would mean, okay, we can analytically continue our big F sort of along this path. But because we only move around half the time, we will never get any problems, right? The definition of branch set is if you can analytically continue along the path. So even if we would have a branch cut sort of over here, that would still make sense. We would just continue through the cut. And we will never return to our original values. So this will always give us a well-defined function f on this integration surface. Okay, so now define lemma as the canvas we have. I will explain this in a moment. So this is just the real part of alpha. Zero notation where alpha gamma is equal to like this alpha r plus I eta alpha r, where for now it's only defined locally, but we will make sense of it globally, so this definition still makes sense. Now it doesn't make sense, but it will make sense in a moment. Where eta, so let's say picture 2 is a vector field locally as in picture 2. Okay, so what does that mean in 2. So we would have eta 2, right? So this is, let's say, eta 1, eta 2. If we are in this situation where A at J star is not equal to 0, must be either this or that. In either way, we would set eta 2 to be equal to the identity. It really doesn't matter what we are doing. but in particular, we don't need to change our integration contour in the second coordinate, so we can say that, okay, here there's nothing. And well, right, I mean, without writing down the parameterization, the vector field would be such that it moves around this, and then, you know, if you want to, you can of course make a smooth over here, smoothing the edges out, if you want a smooth vector field, but it really doesn't matter. So the vector field near this point would look something like this, right? This is the eta1 vector at this point, and at this point, and then we could smoothen it out. Like, so this would be eta1. What this would be? But are you happy with this picture? This is, yeah, you just take a parameterization for the half circle and use this to define the eta1 component of the vector field. Okay, so and eta will be our integration to make sense of f in this limit. So importantly, 2 describes how to define gamma at a single point. Well, and by at a single point, I mean in a small neighborhood of this point, right? But really, this only describes locally. How to define gamma at a single point? And okay, so how do we? So now we want to know how we define gamma along our singularity. So to define gamma along sigma j, how do we do that? So without loss of generality, we can choose our ZP coordinates. Sorry. To define it locally without loss of generality, does everyone know what an atlas is?
Atlas.
Atlas. Okay. Without loss of generality, pick an atlas for sigma j. But it's a bit of a disappointation, I will tell you in a moment why. For sigma consisting of our ZP. Right, so the T would be the atlas of sigma j, and then we would pick transversal direction. So it's really an atlas for some open neighborhood of our singularity in C squared, but does this make sense to you? We pick an atlas would be consisting of, so maybe I can put information marks. But I happy with this. Right, at each point, we can choose this coordinate system for an open neighborhood of that point lying in C squared. We cover sigma j with such open neighborhoods. For each open neighborhood, we pick such a coordinate system, and then we glue them all together, which we can do because we know that the open neighborhood is some open subset of C squared, so that will always work. And then the T coordinate systems will define an atlas for sigma j, because sigma j is a manifold, because G, the defining function, is non-singular. Like, not non-singular, but it's great in never vanishes. So we will never have any geometric singularities on our singularity. So the singularities are not singular. But anyway, this is what we do. And we finally choose that he had the reserves okay. Well, we can choose it whatever we want, however we want, but we have two choices to make, and we choose it such that it is compatible with the orientation of C squared. And we know that the open net of sigma j must be orientable because complex manifolds are always orientable. So we can always make a choice like this. If you don't know what orientability means, it essentially means up and down have the same meaning in this coordinate system compared to this. So why do we choose the coordinate system like this? Well, just so this notion of up and down remains preserved. If you switch the orientation, these pictures will flip. So it's really just convenience. So these pictures I want to keep. So let's like this. Okay, so and after I define gamma along all of sigma j, we have operator. Then and topologically in quotation marks because it's actually like smoothly the same, which is I think for Cauchy's theorem you don't even need smoothness. I think topological is enough. But what I mean is it will not what the picture that I'm about to draw is not the exact same picture, right? Because if you change your coordinate system, like the geometry of this may change, like depending on how you change your coordinate system, but you can always change it back to look exactly like this. Equivalent to the following. Is this the right number? It is. So I will just name it 2.1 and 2.2 again, and once you're nested into this, we will no longer need that. So this is now our z coordinate. In the z coordinate, our singularity, like the intersection of z with our singularity set, will be this point at the origin. And then we have something like this. This is gamma, which is the intersection of gamma with z. And again, this is still local, right? But small gamma is the intersection or the projection rather of gamma down onto the z coordinate. Projection into z. And here we will pass. So this or we will have this. And again, it must be either of the two choices. Right? You can't have more choices because we've already established that there are exactly two choices. And we also know that T will be completely lying on our singularity set. So when we want our integration surface to avoid our singularity set, it must avoid it in the z coordinate. And we know that there are exactly two choices. We know that all of this is a bihomomorphic change of coordinates. So there are exactly two choices. Also, if you look at it in this coordinate system, and because we preserve the orientation, the notion of up and down will be the same. So then here, oops, this would be eta the projection of eta onto z, and here also. So, projection of eta onto z. Okay. Does this make sense to you? Because if this makes sense to you now, we've won, because how can we now define gamma along the entire singularity? Well, we just add all of these local things together. So we may have to maybe change it a little bit, because like if you have two different coordinate systems, it may look different in each coordinate system, but everything needs to be compatible, right? And well, it doesn't, yeah, it needs to be compatible, but you can define it such that it's compatible. So you define it in one neighborhood, and then you define it in all other neighborhoods, and the transition functions between the coordinate systems will tell you how you have to change this vector field eta to smoothly define a surface along sigma j. Does this make sense to you? So if this is sigma j, and if this is my vector field over here, and I can really draw the vector field with an error, right? So then maybe it looks like this here, and well, maybe it will look a little bit like this over here, but I can just smoothly change the vector field. Are you happy with that? Okay. So,
And we know that these singular set sigma j's are themselves smooth because they are the zero sets of some algebraic functions, right? By a
yes, because
So
the Jacobian of
is non-zero.
exactly.
Yeah.
So that's super important. If that is
Right.
not the case, then the transition functions will not
Right.
necessarily
So
be
this poles are have regularity.
yes, exactly. So that's what I meant. Like the singularities
Right.
are not
Regular.
geometrically singular.
Yes.
Otherwise, this would not be possible. But essentially, it's because sigma j is a smooth surface. So we can start with a vector field and then
Construct.
so first we choose this. Then at one point we look how it looks here. And then we patch it together. And that's all. And the notion of up and down will not change, because if it right, if sigma would hit the real axis from above at one point and from the other direction at another point, that would mean that can that happen? Well, it can happen, but if we choose an orientation locally, it will always look the same. I will give you an example for what I mean by it can happen, maybe in the break. But so last point 2, we find gamma on maybe along, right? So we need to define it along sigma j, and then away from it we can just dampen it to 0. We can use some smooth cutoff function to define sigma j along all of sigma gamma along sigma j. Well, okay. And that's how we change our integration. And now we'll break. But probably it's not an example that I should give in the break part. You know what? If you have a singularity set that is a circle, like here, and you have your, so this is in the real plane. So we look at the intersection of our singularities set with the real plane, then we know that the vector field. So eta at each point is a real vector, so we can genuinely draw a picture like this, where we can say that, okay, at this point, eta points outside or inside. And it must be either of the two choices at one point. And also, but now we've defined it by continuity. So that means that if I move around my singularity, the picture will change like this. But now here I have changed the side, right? So if I would look at only the intersection with the alpha plane, with the alpha 1 plane, over here, the vector field eta would point to one side. But if I choose the same over here, it would point to the other side. But of course, if I choose some orientation on sigma j, it will always point to the same set. It will always point to the right of my similarity set, right? The similarity goes here, then along here, it will point to my right, and here it will also point to my right. Just encasing upside down now. But this means that, naively speaking, the notion of up and down in the alpha 1 or alpha 2 plane is not always the same. But we wouldn't expect it to be the same, right? Because it's not intrinsically linked to our singularity. But if we choose some orientation of a singularity, then we can say what it means to be up or down in that coordinate system, and that is it. But yeah, to illustrate, it will change. And of course, I can also, I have the same picture, but I can change the orientation of my singularity, then it will point to the left. So it really is super subjective. But yeah. But all choices will be the same as the picture. That's the important part, really. But if you change the orientations, then you can transition between all of the coordinate sets from one integral to another, and then if you change the orientation, you will get the minus of the integral. So the integral will really remain well defined, simply because your integral does not depend on the coordinate. So even if we define everything in coordinates symmetrically integral, we know how to change the integral. Yeah, via a change of coordinate system. So it really is enough to make it locally and then patch it up together. Yeah, sorry, it's a bit dense, maybe. But yeah, so maybe this is just an example would be you could have one f equals 1 plus right? This would be an example that you have the circle like this. The circle will be done as this is 0, so then it will just be within the circle. And using the procedure we described, you can look at each point how you have to change the x and you will yeah, you should find this picture. I'm not sure if it's this picture or the other, but like you will find either this or this, and you will also find you can repeat it independently on each point. You can confirm that indeed it will stay the same. So yeah, that is.
It's tight and severe.
Yes.
So Valentin, how many lectures do we have left?
Today and next week, and that's going to be it.
So next week is going to be the 19th. So the 19th is going to be the last day.
Yes, which is also why I'm maybe going a bit fast today, because I want to get to application. But I think we can get to the applications because.
So are we going for a year to celebrate the end of Valentin's course? Yes.
Sure.
That would be nice.
Yes.
So maybe we can do this next martedì prossimo, diciamo. No, una pizza, come volete. C'è un ristorante che ho scoperto recentemente che si trova a Porta Lame, una vecchia trattoria napoletana con un gigantesco che secondo me fa la pizza. Diciamo così, migliore che conosco, perché Giovanni è fastidissimo. Voi la conoscete? Allora, ok. I miei amici venivano. Ma non è un vero nome, perché è un nome perché quando loro erano studenti il secolo scorso, una volta un fuoco uscì dalla vicina e dovevano spegnere un ventilatore che ha parecchio su e per arrivare all'interruttore lui prese un mescolo Però nessuno si è mai sentito male o insomma, solo in realtà un attimo che non mi ricordo.
Cioè io forse non lo conosco, però forse l'ho sentito di questo mondo.
Come scritto al rosa. We're talking about celebrations next Tuesday.
Okay.
To go, to go. Remember, we were talking about going for beer or pizza
Yes, yes.
on the last day of
Sure.
class.
Yes.
Not during the last class, but after.
Yeah.
So we were thinking, I was asking them if they know this pizza place. What is the kind of?
I know the pizza place, but it's like extremely incorrect and it's good.
Well, we were thinking of the more.
The pizza people.
So,
But I don't know
let's see if I can find. Otherwise, no, I was thinking pizza. What do you think? Again. Good.
So hopefully by next week I will
Absolutely.
be done.
Let's see.
Because if you remember on Tuesday evening, we have a dinner with the other PhD students.
Ah,
It's on next Tuesday.
so I found a place. So we could do another day. I mean,
Yeah.
so I'm putting this on the chat. But we don't have to go here. Okay, it's just the place that I have in mind.
No. Because that's
Sorry, I forgot.
We have a student dinner next Tuesday.
yeah.
That's
Or another
But it would be nice to do it after, right? When you go for lunch, it's going to be at class time, right? Or how about we do it on Wednesday? Let's take it, let me take a look at.
Point for the interruption, but I forgot to say that we assume that the defining function will always be here to different real parameters. So the polynomial is real coefficients. Not that it really matters for the discussion, but it will matter.
Or would we have a little bit of flexibility and possibly do it the day before? Even because the week after, we're all done. How about Monday, the 18th? Would that be possibly also an option?
Yeah.
Before the image.
Was that?
So we are
I know, but you see, on Tuesday, the 19th, they have another activity. Wednesday, the 20th. I have some meeting.
This for Tuesday evening, but if you want to go, for instance, beer, we have time to get you.
We could do a beer with like happy hour.
Yeah.
And then you guys have your social event. Maybe we could do, so let me, can I come back to you in a few days?
Yeah.
Because I might have visitors that arrive Tuesday afternoon. At the moment, it looks like they're not coming. But we need to confirm everything.
Yeah.
Anyway, I sent the restaurant link to the chat. I'm curious to know as well. If you know the place and what to know the evening. You or not. If not, I mean, you have it something, right? But it's,
Yeah, maybe, but never really.
so the lady who manages it, she is arrived. She should have her own comedy sketch somewhere. It's very well done.
Let's continue.
But so we go for beer. I will.
Okay, let's continue. So this was not really important for now, but it will be important. Otherwise, the picture that I'm about to draw will not make sense. For all the examples that we have in mind, this will this will be true. Also, why is it important if this would not be true? I said last week that the ZT coordinate system also defines a change of real coordinates. That only works here. This one.
Okay.
So I told you, I'm not sure if I wrote it down last week. I think I forgot it. So this is.
So you want to say real valued as opposed to complex valued? Is that what your emphasis here?
We plug in real value.
Ah, they take the reals to
Yeah,
real,
so the coefficients are
real values
exactly.
of this. Polynomial.
So then, but then this, then we know that the intersection of our singularities and will be playing will be a smooth curve.
Okay.
Because then it will be the singularity set of some equivalent. Real curve. So now we can draw a final picture, which will be the picture that we will keep using. So we now look at the real plane, which is the plane that we are interested in, because that's where we originally integrated over, and we are then interested to see, okay, how do I have to change my integral, the real plane, to something else? And how do we visualize it? Right? We can draw the intersection of our singularity like this will be a curve, given this assumption. And then we know that either the vector field theta points to this direction, or it points to the other direction. And this picture is completely accurate in the sense that eta is a vector field from the real numbers to the real numbers. So we can really draw at each point of sigma j dash the direction to which it points. And then, because we can find it by continuity, if we know it at one point, we can really speaking just carry it along our singularity set, right? So we have it at one point, and then we carry it on it. But if we have one singularity, you can think of it as just being orthogonal to it. But it doesn't need to be like that, right? So we could change theta to point like this, and as long as it is never tangent to sigma j dash, this will still always define the perfectly valid integration surface. That would just correspond to maybe, you know, I think it's fine a little like this, and you could smear this out. But as long as you are never tangent to it, it will always work. As soon as you're tangent to your singularity, you would have a situation like this, and then the blue line would lie on the singular point. So this can never happen. But it should be clear that it can never happen, because if this can happen, then it would mean that I can go from this picture to this picture smoothly, which I cannot. This is our singularity. So if I want to change from here to here, I would have to pick up the rest. If it was a polar singularity, and if it was a branch that it, yeah, it's not even clear that we can change from this. So we can do it like this, and what we also do, this is not only an accurate picture, but a small nostalgia. We draw a little bridge symbol, so this is the name bridge and arrow like this. And this is not an accurate picture, and we really just keep it for nostalgia to visualize how to change the integration surface. But this arrow, eta, is accurate. This completely tells you how you have to change the real change.
So Valentin, so
Yeah.
you're thinking of the blue picture as living in, say, 3 dimensions now? The blue
Yeah.
thing? I mean, it's not like we're making a channel around sigma j or sigma prime j.
Exactly what we do.
We're making a channel, so I'm thinking of it in the half channel, but I'm thinking of it in 3D, the half channel.
Yes.
And we need a third dimension.
Yeah,
for that.
yeah. But it's so this is why I mean this is not accurate, because if you have a intersection of singularities, trying to visualize it in 3 dimensions will not help you.
Right.
Because we would have one point with one grid,
No,
one
no, right,
tree
yes.
going in one and the other in the other direction. So this is why if you want to work with it, use eta. But the bridge is just for nostalgia.
Oh, that's the bridge.
Yes, so this is the bridge and this is the error.
Ah.
So why I don't know is because if you want to retain this, this will always have both. Also, it looks nicer to, to have both. But really, this is sort of like a residue because of nostalgia, because that's what we wanted to visualize. But really think about the vector that will. But probably it's preference, but I think using the vector field to understand it is making it easier. And yeah, we can carry it along, and so we can carry the bridge and we rotate it and rotate. Okay. And we can rotate this symbol as long as eta is this. Okay, so this is important. So we have either of the two configurations, and the bridge is always pointing to the left of the arrow, right? If you think about looking in the direction of eta, then we draw the bridge like this. So because the arrow is where you can, if you make this convention for the bridge is safe. Okay, so properties. Do you know what transversal and tangential intersections of submanifolds are? Transversal and tangential intersections.
I used to know that, but it was a long
Okay,
time.
so we will write down the
Okay.
definition. But first, I will write down the properties and then I will write the definition. So if sigma 1 and sigma 2 intersect transversally at a point alpha star. Well, let's say bridges. So I will just say bridges, but it's always bridge and arrows. Then bridges along sigma 1 and sigma 2.
So if they intersect like this instead of this.
Exactly.
Okay.
So yes, exactly. And this is pretty much all that we need to know for what it means to be a transversal intersection. If we have one singularity like this, and another singularity like this, right? This is again. So whenever I will draw a plane, it will from now on always be only a plane. Then I can have this or this, and essentially what it means is I can carry the arrows
Oh, so
through
the vectors eta 1 and eta 2 are linearly independent.
Exactly. So I can choose it. It doesn't have to be like this, right? They could be dependent. You could think about it like rotating them around such that they become.
But you don't.
But the important part is it does not matter. we can carry this through this intersection, and we can carry this through this intersection. And it does not matter. Like when this points to one direction, it does not influence whether this points to this or this points to the other direction. And now it will be clear why we want to keep the bridge. It just looks nice in the picture. But the idea is you can carry the bridges through the intersection, and this will not influence that. And then, of course, at this intersection point, if we look at something like this, where you say this, and this, it would mean that at the intersection, eta points to this, right? This only tells you the direction onto which gamma points, but we have one integration surface in the end. So we need to say at the intersection point into which direction eta points, because we only have one vector field, not both. So what this really tells us is that the vector field that describes our integration surface must point to this direction for this singularity and to this direction for that singularity. So you can just add the vectors up, and that would give you a well-defined vector field. Right, so it would sort of look something like this. This would go like this, and it would go like this. But the point is, if this goes the other way around, well, then I have my arrow pointing like this. So you can see, like, no matter what configuration you choose, you will have it pointing into either of the quadrants. But you can completely do it independently. Like, of course, it will influence how the integration looks like by definition. But pointing to this side does not influence whether it points to this or that side, or the other singularity is the same thing. You understand that?
Transversely means just
Transversally means that we can choose our z and t coordinate system such that the z coordinate for one singularity is the t coordinate for the other singularity. Right? The idea is that you can notate them, visually speaking, such that they are orthogonal to each other. So you can have one singularity where your coordinate system lies like this, and on the other side like this, but you can make this the z coordinate for this and the other way around. If you want to be more precise, I could say that if you have that the sum of the tangent spaces at this point makes up all of C squared. You look at them as a submanifold within C squared. So you can take the inner sum of the tangent spaces because they are sub-vector spaces of C squared. And then the statement that taking the sum of the two tangent spaces is all of C squared makes sense. But I will write it down in a moment. So transversal, it means that can. So if I write it like this, it's like I can choose it. Can choose that one, P1. Maybe let's say it's sigma 1 and T sigma 1. And then sigma 2. Sigma 2. Such that at alpha star, which is our which is in the intersection, we have that sigma 1 equals T sigma 2, and that sigma 2 is T sigma 1. Right? Because these are coordinate systems of an open neighborhood of the C squared. This gives you that the sum of the tangent spaces makes up all of C squared. But this, for this definition, you don't need any knowledge of manifolds or stuff like that. So that's how we define it, how we think about it. And 2. with sigma 1 and sigma 2. Give me a second. Essentially, that I got two. Although using this definition, it is reasonably straightforward to prove that you can carry it around along, right? You would have a picture of something like this. You could draw a picture like this. And then no matter what you have, it will always. But you can use the same picture for both describing the sigma 1 and the sigma 2 singularities, because this will be T of sigma 2 and this will be T sigma 1. But if they intersect tangentially, the bridges must agree. What do we mean by tangentially? If it's not transversal. And the best formal definition, the best actual definition I can give you is the tangent spaces. So the picture would be this. And so what this says is that if the arrow points in this direction on sigma 2 dash, then it must point in this direction too. So if this, so what it says is you can't have a picture like this, because if it points in this direction for sigma 1 and in the other direction for sigma 2 at this point, it would mean that, well, if you take a linear combination of this, then well, it would still make sense to take a linear combination of the vectors, but essentially, if you have something like this, if the tangent spaces agree, then you can choose a transversal coordinate system for sigma 2, for example. Figure out the bridge at this point. Then you forget about sigma 2 and choose a coordinate system for sigma 1. And you already have figured out your coordinate system, and you will find that because they are how do I best explain this? Well, essentially, because you draw the same picture, right? You have a tangential coordinate and you have a transversal coordinate. You can't choose the tangential coordinate for both simultaneously. That would have to collapse them. But you can. Well, I don't know how unhappy you are with differential geometry, but essentially you can choose a coordinate system that maps your manifold onto the tangent space, right? That's the inverse exponential map in geometry. You use that map to define a tangential coordinate system for one, and you use the same, like the exponential map for the other singularity, to also map it onto the tangent space, but the tangent spaces have to be the same. So if you know the direction, how it points away from one tangent space, visually speaking, you already know how it must point away from the other tangent space. And using the exponential map, like to flatten out your manifold onto the tangent space, you already know that this already, like if you know it for one singularity, you know it for the other singularity. Because if you know your tangential coordinate, you also know your transversal coordinate. Because there must be orientation to the coordinate system. And well, I guess this depends. Okay, to be more precise, if it is tangential, if the intersection is tangential, and at this point they have the same orientation. You could have this being one orientation and this having the other orientation. So the orientations must be compatible in the sense that if you identify the tangent spaces, you will get the same orientation of the tangent space. The picture will say the same no matter the orientation. Does it make sense to you?
I mean, I don't know a lot of differential geometry, but it does make sense to me. I mean, I just think of in the first scenario, these two manifolds, sigma 1 and sigma 2, have tangent vectors that are, there is a coordinate system where the tangent vectors are linearly independent.
Exactly.
And in the other one, they are linearly dependent.
Exactly. Exactly.
You know, they could go in the same direction or they could go in opposite directions, but
Yeah, but yeah, and that would be like depending on your orientation.
Right.
Exactly. But also for all examples that I know you don't need all the differential geometry machinery. Like
right. I mean,
you can take two polynomials and look. It's not so complicated. You don't need to know all of the general theory. You look at two polynomials and work it out by hand. It's not like you need all of the tangent space.
The theoretical machinery.
Exactly. If you're unhappy with the word tangent space, think of the velocity vector of this curve, right? You parameterize this curve, you take the derivative, and the velocity vector will both point in this direction. Okay. So that's how we change integration surfaces. And
so are you assuming always that the sigma 1 and sigma 2 intersect transversally?
no.
No, you don't. So you're allowing also for that kind of.
Absolutely, yes.
Okay.
We will see that in practice too.
Okay.
And then well, that's why I try to read it all. Right? So that's how we define our function in this limit.
In this limit. So you don't have 0 plus, 0 minus anymore?
Oh, it will always be.
It will always be plus.
Yes, it's always plus.
Okay.
Yeah, but we assume that kappa is positive.
Hmm.
You can repeat the same procedure
I see,
for
I see,
the
I see,
negative.
I see.
It really doesn't matter.
Okay.
But we assume that it's always positive.
And
this
for,
has
and for us now, gamma is the where are we?
gamma is what we have. Gamma is the bridging error.
Ah, it's the bridging error. Okay.
So gamma is the surface that
Ah,
defines
okay,
the bridging error
okay.
configuration.
All right.
Right. So these pictures define an integration.
All right.
And really, that's important. It is enough to draw this picture and to draw the arrows. Well, once you figured out the arrows, but then you can, right? If you have a picture like this, and assuming you found the arrow here, you know if this is the tangential crossing, then you already know how it looks over here. So you can carry this. You don't have to figure it out here again. And then, if you have an intersection like this, well, you know because this crossing is also tangential, then it must look like this. Well, but then you know how it looks in this intersection already. So even though tangential crossings are maybe a bit more difficult to understand theoretically, practically it's super nice.
It actually
Because
rather than transversal crossings, they seem to be in terms of defining
yes.
these vectors.
And when you know this effect of theta, you know gamma. So this picture will tell you how to define this here too. And again, there are exactly two choices, right? It can be either this or if it would point like this, it would point in the other direction everywhere because it's all connected using this tangential intersection. Okay. So I have 10 more minutes left, which is absolutely amazing. Because that means we can probably get to the applications of everything actually. So, but for now, this is only how to make sense of an integral in this limit. Now we want to understand, assuming we have an integral like this, how can we estimate it? So, how can we estimate it to be Fourier integrals? And by truly Fourier integral, I mean integrals of this type. So, maybe I should have written Fourier type integral, but the philosophy is really, we look at these integrals and we want to estimate them. Okay. Also, everything that I do today is taken from 2 papers, and I will send you the links to them later on. I think that some they are like about 60 pages, so it's not straightforward to prove all of this, and that it really all works like this. So it's really just normal, but theorem. And in particular, I will not prove this theorem. Can be estimated as okay, how do we get this? So for almost so this is just saying direction x point. So for almost all observation directions, the terms in this series up to exponentially decaying. So we are interested in everything that does not decay exponentially. Up to exponentially decaying terms can be obtained by estimating this interval near, and I will find only one second moment, but you can obtain the estimating series by estimating this integral near okay. I will define what contributing points are.
Contributing points.
Yes.
And Valentin, what's an asymptotic series? Is it, you mean like an infinite series? Or
Yes. It's well, it doesn't need to be an infinite series. You just assume that you get some f of x equals maybe something like this. And x goes to infinity. So asymptotic series would mean that you get something like this equals something like some other stuff, such that, so let's maybe call this f for series. Right.
But the other f on the other side, is that the Fourier? Is that the
No, it's just to give it another name. We don't know what this is. This is what we're trying to figure out.
Yeah, and I was just wondering about the terminology asymptotic series. I mean, I know what a series is. I don't think I've ever heard of the word asymptotic.
It's a series that satisfies this relationship. If I take the quotient of f with the series or the other way around, this limit will go to 1 as x goes to infinity.
So it's not exactly a series.
It's not exactly a series. It just happens to be a
asymptotically.
Exactly.
If it's a series, only asymptotic. You cannot. I see.
Exactly.
You cannot represent it as a converging, exactly as a converging series.
Exactly.
But the error that you make.
But the error that you make decays exponentially.
I see.
So if we want to obtain meaningful physical information, we can ignore that.
I see.
Like meaningful physical information about the path.
The error that you make, you mean by making the quotient as opposed to the difference of the two.
Yeah.
I see. The quotient goes to 1.
Yes. Well, the difference would go to 0.
The difference would go to 0, of course.
But what the difference goes to 0, it does not matter how fast this decays mathematically. So saying that it decays exponentially is really good. Like that's the best you can hope for if you are interested in understanding some f far away from like your obstacle, for example, physically, then estimating it up to exponential decay is all you can hope for.
Mhm. So what you're saying is that in general, this boundary value f of x0 is not, say, a real analytic function, because it does not admit a series exactly a series
Oh, I
representation.
see.
But it's asymptotically analytic in that sense.
So it will be real analytic, but what we say is that we can approximate it as something where you have stuff remaining plus whatever remains decays exponentially.
Okay.
So you can have a real analytic function that does not decay exponentially.
You can have a real analytic function which does not, whose remainder does not decay.
Yeah, like any polynomial will grow. Like,
right, exactly.
without bound.
So you can have a real analytic function whose remainder does not decay exponentially.
Absolutely.
Whereas for these,
So I quickly want to tell you what a contributing point is,
Okay,
because
okay.
without that it doesn't,
Yes.
it's not, it doesn't make sense why this is important. If you omit, so let a star in a spread. If there exists a neighborhood U star of alpha star in C squared, that F local of x, which is this integral, right? You just look at the integration
Locally.
exactly. Yeah, so if there exists a neighborhood such that this decays exponentially, then alpha is non contributing. Otherwise,
So that's the definition of contribution.
and otherwise it is contributing.
So if it decays exponentially, then it is contributing.
Yes, and this is a super important definition because I will write on the theorem and then we call it a day. But this theorem is what allows you to really put this to practical use. So the theorem, which I will not prove, I will outline the proof of this maybe next week. Contributing if one is non-contributing. Is non-contributing if is non-singular. So if it's not a singular point, then it is not contributing. Because you can just change your integration surface such that f decays exponentially, right? You can change it such that this decays exponentially. So whenever alpha is non-singular, you will always get that this decays exponentially. Or two, alpha is an intersection of two singularities, but it only belongs to tangential intersection. So if you have an intersection of singularities that is only tangential, then it does not contribute. Well, what is only like if it is tangential, then it is not contributing. So you don't need to worry about this point. Or we should have written down the third one before that. If is only one. So if you don't have an intersection of any kind, then it's possible computing. And I should have written it down the other way because this implies that. Because at this one point, when it's tangential, it is essentially a single singularity because they touch tangentially. So if it is one singularity, it's not contributing. If it belongs to tangential intersection, it's not contributing. And for all of these three, we need that it is not a subtle.
What do you mean by it's only singular or one?
It does not belong to an intersection. So alpha is in sigma 1, but alpha star is not in any sigma j when j is not equal to 1. I will quickly tell you what a subtle is and then we'll stop. We keep this down. Let x be orthogonal to sigma j at alpha star, then alpha star is we have a very nice abbreviation for this. We call it a subtle on a singularity SOS. So it's very remindable. And yeah. Then alpha star is SOF if it is greater than 0. If you take the scalar product of your observation direction x tilde with the vector field eta, and if that is greater than 0, then what this theorem says is we can never change our integration surface to make this smaller than 0. You would need to have this to be smaller than 0 for this integral to decay exponentially. And what this says is that if x is orthogonal to your singularity, and this is greater than 0, then you can never change it.
So that's
that it
for
becomes
all
smaller.
eta, for all choices of eta.
Well, if it is for one choice, then
Then
it's
it
for
is
every.
for all the other choices.
Because to make it smaller than 0, you would have to make it first tangential and then
then
move it through it. And this you
And
cannot
that's
do.
not.
But of course, you can have orthogonal observation direction, but eta pointing in the opposite side, and then it would not be
I see.
a subtle. I think we'll stop here, and next week I will give you an outline of the proof, but really I just give a sketch, and then we will see two theorems, namely the first is